Okay, so week 5 stuff. This is essentially going to be electrocyclic reactions, and to start off, basically the foundation of them are the molecular orbitals, these infinity-looking loops. And so whenever you're doing this, sometimes you'll see HOMO and LUMO being thrown out. Sometimes you'll see excited versus ground state. So we're going to go ahead and walk through those. First things first. Whenever you're just looking at any kind of, and let me just make sure this is, oh, hold on. Oh, we'll do, that should be better. Yeah, hopefully that is a little bit better. So anytime you see, let's just say, for example, a multi-alkene compound, so you just have a diene in this case, and then you're asked how many molecular orbitals are these given. Basically, the number of pi electrons equals the number of orbitals you work with. So in this case, if we had 4 pi electrons from a diene, you would have 4 orbitals. And then 6 pi electrons from a triene would give you 6 orbitals. And so the orbitals are just the fancy term for whenever you're kind of just making the HOMO-LUMO chart, it's just these little like dashes on the bottom. Let me just make sure that's focused. Okay, cool. So whenever you're doing these, for example, let's just take a diene. We know that there's 4 pi electrons, meaning you're going to have 4 orbitals. So I would just begin by drawing out 2 different states, ground state, I'm going to separate this out, versus excited. Okay, and then you're going to have 4 orbitals, so 1, 2, 3, 4, 1, 2, 3, 4. Okay, so these are essentially the orbitals that you're looking at, right? And so sometimes you're going to see these squiggly looking things. Essentially, they're just how the orbitals are notated based off of your nodes. So the key is the nodes are just how you would split the orbitals, right? So whenever you're doing this, let's just, for example, this is the diene we're going to work with, right? Regular diene, we have 4 pi electrons to work with. Therefore, you just kind of go along the list of, well, actually, first we should probably, let's explain what ground versus excited state. Ground state, essentially, the electrons have not been altered. There's no use of photochemical energy. Nothing has happened to them, right? So they're just ground state, neutral state. Excited state means that there has been basically a photon of light that's affected one of the electrons and it moves up a level. Only one electron moves up a level. Therefore, whenever you're looking at this and you're just kind of going along the list of filling in your electrons, you just kind of go by Aufbau's rule, and then you just fill in 2, 2, 2, going up with however many electrons you have. Ground state, we said there's no alterations, so that's why you just have 2 different spin electrons as you go upward. And so we have 2 and then 4, that's it. We don't have any more electrons to work with, so that's fulfilled. And then for this excited state, remember, you're going to basically take 1 electron from the highest state of the ground state, essentially, the HOMO of the ground state, which in this case is, we're going to just number these levels. So 1, 2, 3, 4. This psi unit is just a fancy, just level designation thing, so don't worry about that. Just to denote the levels. Whenever you're talking about HOMO, remember HOMO equals the highest occupied orbital, okay? The highest occupied molecular, obviously molecular orbital, but yeah, occupied. Occupied means has to have at least 1 electron, okay? It has to have at least one electron in it. Of course, is the pi electron. LUMO, lowest unoccupied. Now, the lowest sometimes confuses students. Remember, lowest could mean a pretty high level. It just means whenever you're going down your list, your list of orbitals, your levels, whichever one has no electrons, right? So LUMO will always have 0 electrons, always. This is for sure because it's an unoccupied orbital. However, HOMO has to have at least 1. And why I say at least is because in the difference between the ground state, if you go up your levels, if you're examining your levels, 1, 2, 3, 4, the highest level that's occupied, level 1 is occupied, but it's not the highest. Level 2 is occupied, but it is the highest, and there's none in 3 and 4. Therefore, like we said, 0 electrons in the lowest unoccupied would be this state, because again, it's the lowest of all the levels going downward that has no electrons. This is a lower level, correct, but it does have electrons, therefore it can't be the LUMO. This is a higher level than 3, and both have no electrons, therefore 3 is the LUMO. So hopefully that makes sense. HOMO, the highest occupied. We've already designated the LUMO to be above the HOMO. That's just the kind of relationship that they share. So I guess if you forgot one day, the HOMO would be underneath your LUMO if you identify the LUMO correctly. But for the sake of understanding what HOMO is, highest occupied, 1 is occupied, 2 is as well, but 2 is a higher level in terms of orbital leveling, so 2 is the HOMO. Now excited state, again, it's HV, and then thermal, heat would be for ground. So you need light, photochemical energy, to excite an electron. So the first 2 electrons will stay the same, and then the electron of the HOMO in the ground state will actually move up 1. That's why this kind of relationship exists. One of these guys gets stolen and he moves up here. So now your LUMO, the lowest unoccupied, levels 1, 2, and 3 are all occupied by at least 1 electron. Therefore, they have the ability to become HOMO, but obviously you have to decipher which. LUMO 4, level 4, is the only one with it, okay? So that's has to be the LUMO because it's the lowest level, even though it's level 4, but it has no electrons. Every other level has electrons. Now, examining the ones that do have electrons, 1, 2, and 3 do, but I'm looking for the highest level. Therefore, it has to be level 3. So that's why the HOMO's level 3. Highest occupied with at least 1, okay? With at least 1. And honestly, I should show this one in a different spin. Oh, and again, these actually, I'm sorry, these should all be single-headed arrows because we're talking about electrons here. So just for the sake of correctness, these should be one-headed arrows, okay? So anytime you're asked on the exam, you do need to draw them one-headed arrows, and now you understand the difference between ground and excited. Excited uses light, ground doesn't, so it's just thermal, and the HOMO is 1 above. The HOMO and the LUMO are both 1 above in the excited state, if that makes sense. Now, you might be thinking, well, what does this have to do with the ugly looking orbitals? So if we're gonna kind of go across here. So in terms of 1, 2, 3, and 4, you're always gonna use the HOMO orbitals whenever you're doing this. And again, the rule for the nodes is basically the number of nodes you're gonna add in between these orbitals is gonna be n minus 1, and n refers to your level, okay, where n equals the level of the orbital. Therefore, level 1, 1 minus 1 would have 0 nodes, so 0 nodes. Level 2, 2 minus 1 will have 1 node, so and then we need to make it a symmetric idea. So for the first one, I'm just gonna have all of these guys on top shaded. It's okay if you start on the bottom, but for the sake of just consistency, I'm gonna start on the top. Now you need to basically, the nodes will flip your orbital shading notation. That's essentially what the nodes are responsible for. So in that case, these guys will flip because the node essentially creates a line of symmetry in between them. This is a much more simplified explanation, but for the sake of, explaining it. Yeah, now we have 3 minus 1, so we have 2 nodes, and then 4, we're gonna have 3 nodes. And you'll see this at the top of both the 6 pi electron chart and the 4 pi. The top part should have a bunch of nodes, basically 1 after each, making them into different orientations. Now, in this case, just remember, make them symmetric. Boom, 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 good. And then you have 2 nodes satisfied, so then 1 node, just for the sake of it, 2 nodes, and then 3 nodes, right? And these will all be different. Now, you're wondering, well, why do I need these? What's the point? Well, if you go back to your reactions, right? So you're gonna basically be using these for your electrocyclic reactions. And remember, electrocyclic reactions are different from the sigmatropics in that the electrocyclics will look somewhat like this. This is the common for the 4 pi, and then the 6 pi. Oh, that is not a hexagon. Will look like this. Boom, boom. No, I'm sorry. I cannot draw. Hold on. It should look a little bit like this. Boom, boom, boom. Okay, so sometimes you might be, after learning about the sigmatropic and everything, you might be like, oh, well, how do you differentiate? The 4 pi, electrocyclic is pretty characteristically looking like basically an opened square that's missing one. This guy will look like an opened octagon more so an open octagon, and then you'll have to fix them into a hexane ring again. But the products will always look like either a 4-membered ring with an alkene and a hexagon with an alkene bond. That's, I'm sorry, not these. We need to have 2 because we had 3 alkenes in the beginning. These will always be what the final product should look like for these electrocyclic reactions. You just have to add on stuff, if that makes sense, right? So in terms of explaining where these nodes and where they kind of fit into all this, you're going to always use the HOMO of whichever state you're determining, right? So in this case, if you were to be given thermal, which is the triangle similar for heat, you're going to use the ground state HOMO. You always use the HOMO, by the way, because it's the only level with electrons that are usable, right? So you always going to use the HOMO. Whether or not it's ground versus excited, you have to determine that based off of the symbol used. This is the photochemical, and then this will be the excited HOMO state. Okay, from there, now you've identified these patterns. So looking at the HOMO, back to the orbital theory. Whenever you're doing these, you do have to memorize. This is more so kind of a chart that's been made out of ease of understanding, and you're going to use these 2 orientations, and then this will be the conrotatory, disrotatory, and I'm sorry, the way I'm filling this out is probably confusing, but it's just how my brain works, to be honest with you. Disrotatory, good, and then in, and then out, in. And this is also out, as long as these are kind of the same. This is pertaining to the groups on carbons 1 and 4. Hopefully that's seeable. Oh, sorry, let's scroll this up. So, well, carbons 1 and 4 refers to these guys. Carbons 1 and 4 refers to these guys. Whenever you're doing, what's it called, the reaction. So it'd be these 2 as well, and then boom, boom. The ends of the conjugated regions. Remember, the ends of the conjugated regions are your essentially where the outside groups are going to attach to, right? So this is what it's referring to on these guys. I shouldn't have labeled it here, but these guys, okay? This is what I'm referring to with the in and out. And I haven't drawn any here, but like if, for example, here, this would be an out group because it's literally pointing out. If I was to make the ring, also my reasoning for this is, anytime you hear out versus in, just think if you were to complete the ring, which way would it point? Would it point towards the creation of the ring? Like this section, this would be inward. As you can see, it's in towards the ring's formation. Outward is more so, it's just pointing outside of the complete ring. That's the basis of in and out, if that's a little helpful. But yeah, back to completing the chart. In my opinion, understanding the chart will, memorizing the chart will make your life easier, but we're going to explain how this chart comes about. But for example sake, okay, cool. Now, whenever you're picturing the molecular orbitals, say for example, you've taken, and also the molecular orbitals, these guys that you use, also these should be memorized. Conrotatory being that they move in the same direction in order to butt heads with each other. And what I mean by butt heads is that these 2 shaded regions want to move, like say shaded region on, oh, that's probably a horrible idea, but on top, but they want to butt heads with each other to where they're horizontal, if that makes sense. So that's the whole basis of why these are, like why this chart works, because it's set in stone on how these 2 reactions would kind of just take place. But this would be disrotatory, meaning that these would actually flip the different reactions, right? So essentially they would go inward, which would be just kind of the same on the bottom, but it's just different directions. Disrotatory means different directions, conrotatory means the same direction. And remember, your goal from this is to make them butt heads with each other. So this is your end goal. You want them to be in this orientation. That is the end goal if you're trying to understand molecular orbital theory. That's what you want. This from them being like that. So you would have to move them this way, inward, and this is, again, conrotatory because they're moving in the same direction, if you were to draw the arrows completely, in order to do this. And this is the same for this, same for 4 pi light, 6 pi heat, except disrotatory, they move inward to the same, to the different directions because you want the heads to butt each other, right? And you get this essentially from the terminal carbons of the HOMO of whichever state you're using, right? So for example's sake, if I was to give you like, 4 pi heat, right? 4 pi heat. And then if we look at the graph, right, so 4 pi heat, okay, and we're gonna look back at our nodes, so 4 pi heat, and heat, remember, refers to ground state. You're gonna use the HOMO, which is our second level. And if you go to our orbitals, these are what the orbitals should look like, correct? So, and I've used, and again, I'm using the terminal orbitals. That is where these guys come from, okay? 4 pi heat, I've used the HOMO of the ground state because heat refers to ground, and I've chosen the outside orbitals from the orbital list, if that makes sense. Now, and then if I was to do that, say 4 pi light, and we see that it's disrotatory, I'm gonna look at the third level because I need to use the HOMO always. Third level, go across, use your terminal orbitals. That is why they look like this. And this will be basically, this graph itself is essentially foolproof. Like this is because based off of the molecular orbital theory. So it shouldn't deviate from this. And then if you memorize all of these, and then in the case you forget the graph, you could always, well, that's probably horrible, but it is what it is. Yeah, that is how you can kind of solve these in a pretty simple fashion. So for example, if after you've memorized this and after you understand this, we'll do both directions. So for example, we've already been over these a lot, so I'll just do a really quick example, but we'll just do a, and remember, you do need to know your reaction arrows for this, but I'm gonna hope that you guys memorize those because it's essentially just pretty simple. Because I mean, just go by the idea of electrocyclic, so they should form, you know, a cyclic pattern, and then thus they will form a ring. Remember, from this problem itself, what we predict, this should be the product always, so it should look like this already, if that helps you. Then you need to draw on kind of the carbons, and I'm just gonna label these again. 1, 2, 3, 4, 1, 2, 3, 4. Keep yourself consistent. Carbon 2 has a methyl, carbon 3 has a methyl. Boom. You already know that this should be a formed bond, and now you have an outside facing ethyl, and you have an inside facing ethyl. And remember, it's because of the kind of their orientation to the ring versus outside of it. It's like in the creation of the final product. That's what I'm referring to. Now, once you've done this, outwards are going to essentially, oh, actually, no, in this case, we're just going to look back at our graph, out and in, and we have a, we're going to do a 4 pi heat system. Remember, this is, you need to know what that is. You need to know what condition you're given, obviously, because you can't decide which one. But say we're given a 4 pi being I have 2 alkenes, therefore 4 pi electrons. Heat, that's just given to you. And then I'm gonna do, and then you kind of look at your graph after you've memorized this. Okay, this is conrotatory. This should be a thing you just memorized. You should memorize this. Conrotatory, and you should place as 1 in, 1 out, cis. So these guys should be cis. And honestly, whichever one you put them on, it's okay. If you put them on a dash, if you put them on a wedge, it's okay. I just put them on a dash just for the sake of being consistent. I don't confuse myself. This would be a meso compound because of symmetry. So no enantiomers in this case. Now, if you're wondering how the orbitals kind of look in this, how you should picture this is if you have both orbitals, and again, I'm going to use the orbitals that are specified that I should use, because if you use these, you will mess yourself up. So remember, you need to stay consistent with this division. These orbital pairs are going to be for these guys, and then these orbital pairs for these guys, okay? So using what I know now from this, and that they're going to rotate this way, when I'm imagining this orientation, you should kind of think of it as, let's say, 1, 2, 3, 4 in terms of carbons. So what I'm going to draw is kind of like, should look a little bit like this, although it's not extremely representative, but just choose the side that's closest to you as the numbers 1 and 2 carbon, and we're going to just keep ourselves consistent, and we're going to do 1 is going to be an outward, and then 2 is going to be like this. Oh, hold on. Apologies, that's probably not clear. Okay, I'm trying to draw an ethyl, but I'm blanking. Hold on. Okay, we'll just do it for that sake. Okay, so this is the outside one. So 1, 2, 3, 4. Okay, so stay consistent with your numbering as well because it will stop you from being confused. So this is the molecular orbital pathway. And then now, so when you're doing this, one of them is outside. So that's why I'm going to draw kind of an ethyl pointing outward. Then I'm going to point an ethyl inward. Why? This side coincides with this orbital. This 1 and 2 coincides with this. So essentially this is carbon 1, 2, 3, 4, if that helps. And then you've done, you've just added on the end conjugated ones. And I don't add 2 and 3 because 2 and 3 are useless. They're not going to move because they're going to end up on an alkene. Don't worry about that. You don't need to know the stereochem for those because you end up on an alkene in 2 and 3. So these, because theoretically you're going to form an alkene later. So therefore, take this and make yourself a little bit of a different kind of angle from it. Now, when you're doing this, remember, you have to just kind of memorize this, but we have 4 pi heat system. We know that the orbitals are mixed matched, they're different size, and they're going to be conrotatory. So they're going to move in the same direction because I want the heads of them to butt each other, right? So what I mean by that is if I'm rotating this guy, he's going to rotate downward, right? So he's going to rotate inward, and then he is going to stay with him, okay? So you just have to kind of rotate the paper like a little bit like this to stay with him, if that makes sense. So this guy will be pointing upward, and then do the same thing for here. And remember, the goal is to make sure that the shaded heads butt heads with each other. And then from here, stay consistent. Draw your arrows again. This guy has moved upwards. This guy has also moved upwards. Therefore, both of them are facing upwards, okay? Both of the outside group, no, not sorry, the outside groups, both of the branches on carbons 1 and 4 are both up. That's why they're cis. Both up, cis. I guess, well, actually, hold on, let's make these wedges because they are both pointing up. If you really wanted to, you could just, you could go by whichever kind of molecular orbital theory you figure out. Like if they're both pointing down, you can put them on a dash. If they're both pointing up, put them on a wedge. That's a little bit of my fault, so sorry about that. But yeah, in this case, put them on a wedge. It doesn't necessarily matter too much, but as long as they're cis, then you're correct, okay? As long as you're cis, then you're correct, because I don't want to confuse anyone. But remember, the only thing I really did, like say for example, I have a different system where it was a 6 pi heat, right? And then I have to use these guys again. Hopefully that's going to be seen. Remember, all I'm going to do, and then for example, let's just put, boom, 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 and then we'll just put this guy's outside, this guy's outside. Okay, so we know that this follows the suit of the table. These guys have to rotate inward, these guys have to rotate inward, different directions, but they look as if they're butting heads with each other. So then the following formation should just look like this. Okay, from there, what's it called? Both are out, right? So this is an outwards group, this is an outwards group, and then you're essentially going to follow suit of this being kind of 1, 2, 3, and then 4, okay? And you just want to keep, just kind of, I would think, here, it's probably easier if I number it this way. Think of the middle carbons, so think of 1, 4. Think of the middles of the orbitals. The middles are going to be your 1 and 4 carbons. Then 2 and 3 refer to the shaded heads, or just the heads that kind of along behind them, because in this case they're not both shaded, right? But just think of them as the other loops on top. So then you're just going to draw your outside groups. So this one's pointing out, this is pointing out. Then accordingly flip them, right? So if I'm moving inwards for this guy, he's going to rotate, hopefully that can be seen, he's going to rotate looking like this on that side. So if I'm rotating him, hopefully it makes clear sense that that's how it should kind of end up, because I've just essentially turned him this way. Turn the figure 8 this way, okay? Then for this guy, also do the same thing, but turn him the opposite way, and you should have this ethyl group, or I'm sorry, this methyl group pointing, should be, boom, good, and then this guy should be like this, okay? So then these are both pointing up as well. So these are both up, therefore cis in the product. That's where we get that. So therefore cis in the product, and then what's it called? Let's see. And it follows suit over here as well, because these are both out, and then that follows suit. Oh, I'm sorry. Yeah. Let's see if that makes sense. Yeah, these are both outwards groups, out, and then I'm looking for a 6 pi heat, cis, which is good. I'm sorry, disrotatory, which is good because they went different directions, and then cis is the final product. So that's why we end up as cis. So if I was to do this with, let's see, heat, we should form like that. And then, oh, I'm sorry. Remember, this is the staple final product that you do. And then from here, we had no groups on 1, 2, 3, 4. We had no groups on 1, 2, 3, 4, other than just 1 and 4. We did have, okay, good, good. And then the only thing we did have was, what's it called? Two methyl groups, and then so they were cis, both pointing upward, therefore they're like this. That's why this is cis. And it's the same thing with here. So this is the molecular orbital theory. This, if you just memorize the chart, okay, 6 pi heat, disrotatory, and I have 2 outwards groups, cis, ends up cis. And the same thing, this is also a meso compound, so no enantiomer. And that is the basis of how you do electrocyclic reactions. They're much simpler once you memorize this chart, but in case you do need to know this for the exam though, for sure. You do need to know how the molecular orbitals are gonna look. So memorize how they'll look with both, how they kind of rotate, conrotatory and then disrotatory, and then you should be good. So that should be all for electrocyclics. Oh, and then we also have cope. I'm sorry, we have the rearrangements. Sometimes you'll see the rearrangements kind of like flattened out in a linear branch. That's okay. I wouldn't be super, what's it called? Don't be intimidated by them. But again, the cope rearrangement, it's pretty straightforward. You're just essentially breaking some bonds to make more stable alkenes, okay? So for example, we have just kind of, let me see, because I'm trying to see this off the other side. Okay, cool, all right, cool. So we have di-substituted alkenes in this case, right? And so the way you would do this is you're just gonna have to break some bonds to replace them. I would just start by creating this kind of just gone bond, like this bond just is not here. Follow suit with your circular arrows, and then of course everything has to rotate accordingly. So you go from 2 di-substituted because 1, 2, and then 1, 2 for the substitution of the alkenes. 2 di-substituted. Then you're gonna go to here, good, and then you're just gonna keep following suit. Now you've created. Then again, I did something wrong. This should not be a bond. Sorry. We broke this guy. Now you've created 2 tri-substituted. 1, 2, 3. 1, 2, 3. Okay. So 2 tri-substituted. That's the cope. It's just essentially creating more substituted alkenes. That's the goal of cope rearrangement. Now, when you get to Claisen, sometimes Claisen rearrangements, they can be kind of just shown in like a linear, let's just say a linear pattern. Sometimes like this, or they can be kind of branched out, something funky like that. Don't be super intimidated, because essentially you just have to create them in a circular but broken ring. What I mean by that is use this foundation, use this oxygen. This is the Claisen again. This is the Claisen. Remember, the regular Sigmatropic does not have an oxygen, but the Claisen does. And then you're essentially going to, remember, you can only rotate single bonds. Again, you can only rotate single bonds, and I'm going to rotate this guy, both of those guys, to essentially form what looks like a broken ring-like structure, okay? So I've rotated him inward, and then he should look like this. Okay, and then I'm gonna put this guy outside. Now, you're probably wondering, why did I put this guy outside instead of putting him inward? If I did it inward, then I'd have basically a fulfilled ring, but I'm missing this bond, which I need for to make a hexane looking like similar structure, right? This bond is essentially what you would create to kind of resonate and make a ketone, right? So in the Claisen, you go from 2 alkenes to 1 ketone and 1 alkene. If you don't have that in your product of the Claisen rearrangement, you've done something wrong. You need 1 ketone and you need 1 alkene. Of course, you'll get an enol though if you have an aromatic ring attached to it, but I'll go over that in a little bit. So just to do this, my tip, break the bond towards the allylic alkene. This is the allylic. This is not allylic because it's too far away. Allylic just means it's on the carbon that's adjacent to the oxygen in this case. Break towards it and then remake that broken looking bond. So make that broken looking bond and then follow through with your arrows. Okay, so follow through with the cyclic arrows, and you're gonna just make sure that everything is correct. Again, you have a broken ring though, so you do have a broken ring. I'm sorry, that should not be, that should just be a single bond. Okay, you've done this, you've done that, good, and then this should be here. Okay, that is what your rearranged product should look like. It's pretty straightforward. It looks more complicated than it is, but I've broken a bond and I've created the one that's new. And even if it looks linear, you just have to kind of like take the linear branch and just fold it into a broken ring that has an outside, that has a, what's it called, a missing bond. Okay, that's what you should do for those. And then in the case that you're kind of giving them like really like just kind of giving it to you just like this, just follow through with it. Just break towards the allelic, You can do it the other way as well. It works the same way. Just to show you, you can do both as long as your arrows stay consistent and you don't mess up, like you don't confuse yourself. You can do either way though, but just to show you, you can do it like this, okay? So instead, say I wanted to break, let's say, and remember you should go to, with the alkenes, right? So you could technically just start by going, and we're gonna remake this. Oh, okay, hold on. Let me just draw this a little bit better. Okay, perfect. So this is the bond that we want to make. So we're gonna just start from here. You can start from here, 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 but you could also start the other way. So you could essentially do here, then this must break, and then this goes this way. They both make the same product, okay? They're essentially the same method, but you need to be consistent with how your arrows are moving, and you should start in a way that's not confusing to you. Just make the ketone at the beginning, in my opinion. Make the ketone first, then follow through with everything else. It'll make your life so much easier. In the case that you need a tautomerization, that's just gonna be if the only case that this happens, you basically, if an aromatic ring is present, do the Claisen as you saw above, do Claisen, but reform the new ketone into an enol. And you might be wondering, what is an enol? An enol is just an alkene that has an alcohol attached to it. Example, that's what an enol looks like. Okay, it's an alkene, that's where the ene comes from, and then alcohol. Okay, so for example, we have just if we add it to like, let's see, let me just make a new one. Let me just use the group work one because I think that's less confusing. Boom, we got this. Okay, there we go. Okay, boom, there you go. Okay, then just do the Claisen as regular. I'm gonna break towards the allelic, and I do have an aromatic ring though, because it's just kind of in the problem, so you just have to be careful. And I want to remake this bond, remake that, and then follow through with your arrows. And then remember to be consistent with your alkenes here, because it can be confusing. So we've made a ketone, but the aromatic ring has been disrupted, and then you're missing this bond. This bond is missing again, so just be wary. Boom, and then you do this. Okay, again, we're followed suit. We have one alkene and one ketone. Now, because the aromatic ring can go back to its former self, you tautomerize, and you should essentially reform the aromatic ring, and this becomes an OH. I don't believe the mechanism is needed to be known, but you do need to understand that if you have an aromatic ring attached to some kind of Claisen rearrangement, oh, I'm sorry, I didn't even show any of that. Oh, okay, well, I'm sorry. But just to kind of reiterate that, I did the Claisen as normal, followed through, broke towards the allelic, kept following, remade this broken bond where it doesn't seem to be. Then you've recreated a ketone. You've created now a ketone and alkene. Then, because you have an aromatic ring that can go back into stability's sake, it can tautomerize. You go from the ketone to the enol. And the enol is just the alkene that's attaching to the alcohol. And this is the same thing. It's just a unfulfilled ring, but it has a aromatic ring attached to an alcohol now. And that's the only difference between the Claisen. This one works just regular because there's no aromatic ring involved. This one does have an aromatic ring, so that's why you have to go back to the alcohol. And this one, you just can keep the ketone and the alkene. And then again, for the cope rearrangements, you just the goal is to basically make the more substitute alkenes. And yeah, that is part 1 of week 5.